Lateral displacement of a ray of light. Lateral displacement of a ray of light due to refraction through a glass slab, through a rectangular glass slab. Lateral displacement of a ray of light due to refraction through a rectangular slab. Let ABCD be a rectangular glass slab. ABCD is the rectangular glass slab on which a ray will be incident obliquely. This is the rectangular glass slab. And now we can draw the normal. This is the normal drawn on the first refracting surface AB of the rectangular glass slab. This is the normal, and a ray will be incident at the point Q on the first refracting surface AB. Here we can show the incident ray. PQ is the incident ray which is incident at the point Q on the first refracting surface at the angle of incidence I1. Here PQ is the incident ray on the first refracting surface AB of the rectangle. Now the incident ray PQ will be refracted along QR inside the rectangular glass slab. The refracted ray will be traveling along QR, and we can draw the normal on the second refracting surface. QR is the refracted ray which will be incident at the point R on the first refracting surface, and the ray will emerge along the direction RS. RS is the emergent ray with respect to the second refracting surface DC of the glass slab. RS is the emergent ray which emerges out of the rectangular glass slab through the second refracting surface DC. Now we can denote the lateral displacement. Here Rx is the lateral displacement of the ray of light due to refraction through the rectangular glass slab. PQX is the original direction, and RS is the emergent ray, and Rx is the lateral displacement. And here small t is the thickness of the rectangular glass slab. Small t is the thickness of the rectangular glass slab, and in this case PQ is the incident ray, QR is the refracted ray, and RS is the emergent ray. We can denote angle of incidence. I1 is the angle of incidence on the first refracting surface. R1 is the angle of refraction. R2 is the angle of incidence on the second refracting surface DC, and I2 is the angle of emergence. We can denote the normals. Qn is the normal on the first refracting surface. Q1 prime is the normal on the second refracting surface. Mu2 is the refractive index of rectangular glass slab, and mu1 is the refractive index of the surrounding medium, that is the refractive index of AR. Now what will be the formula of lateral displacement of ray of light? Rx is equal to T sine I1 minus R1 divided by cos R1, which is the lateral displacement. Rx is equal to T sine I1 minus R1 divided by cos R1, which is the lateral displacement of ray of light due to refraction through the rectangular glass slab. Now mu is what? Mu is the relative refractive index, which is mu2 by mu1, and that is equal to sine I1 by sine R1. Using Snell's law, at the point Q we get relative refractive index of glass slab, that is mu, which is equal to mu2 by mu1. Rx has another expression, that is T sine I1 bracket 1 minus cos I1 divided by 1 minus cos I1 divided by root over under root mu square minus sine square I1. So this is another expression of lateral displacement. Rx is equal to t sine I1 into 1 minus cos I1 divided by root over mu square minus sine square I1. That is another expression of lateral displacement of ray of light through the rectangular glass slab. And this is the expression of lateral displacement Rx in terms of thickness T and I1. So Rx has two expression. Ray is traveling along PQ, QR and RS. And here RS is parallel to PQ and RX is the lateral displacement which has the expression T sine I1 minus R1 divided by cos R1, and RS that is emergent ray RS is parallel to incident ray PQ, and here R1 is equal to R2. Now we can derive the expression of lateral displacement. Let I1 be the angle of incidence of ray of light on the fast refracting surface AB of the rectangular glass slab. I1 is the angle of incidence. I1 is the angle of incidence on the fast refracting surface. On the fast refracting surface of the rectangular glass slab ABCD. I1 is the angle of incidence on the fast refracting surface AB of the rectangular glass slab ABCD. R1 is the angle of refraction. R1 is the angle of refraction. R1 is the angle of refraction with respect to the fast refracting surface AB. With respect to the fast refracting surface AB of the rectangular glass slab. Fast refracting surface AB. R2 is the angle of incidence. R2 is the angle of incidence on the second refracting surface DC of the glass slab. R2 is the angle of incidence on the second refracting surface DC of the rectangular glass slab. Now I2 is what? I2 is the angle of emergence. I2 is the angle of emergence from the second refracting surface DC. I2 is the angle of incidence from the rectangular glass slab ABCD. I1 is the angle of incidence, R1 is the angle of refraction, R2 is the angle of incidence on the second refracting surface. Now Rx. Now we can derive the expression of lateral displacement Rx from the triangle RXQ. From the triangle RXQ, sine angle RQX, sine angle RQX is equal to perpendicular by hypotenuse, that is Rx divided by QR, or comma Rx is equal to QR into sine angle RQX, or comma Rx is equal to QR into sine I1 minus R1. So this is the expression of lateral displacement of ray of light. Rx is equal QR into sine I1 minus R1, where angle RQX is equal to I1 minus R1. Also from the triangle Rn prime Q, cos R1. From the triangle Rn prime Q, cos R1 is base by hypotenuse, that is Qn prime divided by QR. Cos R1 is equal to Qn prime divided by QR, or comma QR is equal to Qn prime divided by cos R1. Therefore, Rx, here QR can be written as T divided by cos R1. QR, the hypotenuse QR can be written as T divided by cos R1, which is equation 2, where T, thickness of the slab, that is T is equal to Qn prime. Thickness of the rectangular glass slab, thickness of the rectangular glass slab is Qn prime, which is equal to small t. Putting the expression of QR in equation 1, we get Rx as equal T into sine I1 minus R1 whole divided by cos R1. Rx is equal to T into sine I1 minus R1 divided by cos R1. That is the first expression of lateral displacement. Rx is the lateral displacement of the ray of light PQ due to refraction through the rectangular glass slab ABCD. Due to refraction through the rectangular glass slab ABCD. Here PQ is the incident ray, QR is the refracted ray, RS is the emergent ray, and here Rx is the lateral displacement which is equal to T into sine I1 minus R1 divided by cos R1. Now Rx is equal to T into sine I1 minus cos I1 into sine R1 divided by cos R1 is equal to T into sine I1. Sine I1 is taken common, under bracket 1 minus cos I1 divided by cos R1 into sine R1 divided by sine I1. This is the expression of Rx. Rx is equal to T sine I1 into 1 minus cos I1 divided by cos R1 into sine R1 divided by sine I1. This is equation 2. Rx is equal to T sine I1 into 1 minus cos I1 by cos R1 into sine R1 by sine I1, which is equation 2. Now, the relative refractive index of the rectangular glass slab with respect to air or with respect to the surrounding medium is given by, it should be glass slab, not glass prism. The relative refractive index of the glass slab with respect to air is 1 mu2 is equal to mu2 divided by mu1. 1 mu2 is equal to mu2 divided by mu1. Relative refractive index of the glass slab with respect to air is sine I1 by sine R1, or comma it is denoted by mu. Mu is equal to sine I1 divided by sine R1, or comma sine R1 is equal to sine I1 divided by sine I1 divided by mu. Sine R1 is equal to sine I1 divided by mu. Now we can find the expression of cos R1. Cos R1 equal to root over 1 minus sine square R1 is equal to root over under square root 1 minus sine square I1 divided by mu square, or comma, therefore cos R1 should have the expression 1 by mu root over under square root mu square minus sine square I1. Cos R1 is equal to 1 by mu into mu square minus sine I1. Now Rx has the expression T sine I1 under bracket 1 minus cos I1 divided by cos R1, cos I1 divided by cos R1 into sine R1 divided by sine I1. Now we can put the expression of cos R1 and sine R1. T sine I1 into 1 minus cos I1 divided by, putting the expression of cos R1 1 by mu into root over mu square minus sine square I1 into sine R1 and putting the expression of sine I1, and that should be sine I1. Or therefore t sine I1 into 1 minus cos I1 divided by 1 by mu root over mu square minus sine square I1 into putting the expression of sine R1 by sine I1, that should be 1 by mu. Therefore Rx is equal to, should have the expression t sine I1 bracket opened 1 minus cos I1 divided by root over mu square minus sine square I1. So this is the another expression of lateral displacement. Rx is equal to t sine I1 into 1 minus cos I1 divided by mu square root over mu square minus sine square I1. That is another expression of lateral displacement of ray of light due to refraction through the rectangular glass slab. Lateral displacement of ray of light through the rectangular glass slab due to refraction through the rectangular glass slab. Now we get the expression of Rx in terms of thickness of the glass slab and angle of incidence I1. So this is a rectangular glass slab through which a ray will be refracted along this direction, and this is the incident ray. The ray will be refracted along this direction, then it will emerge out along this direction, and in this case a ray is refracted through a rectangular glass slab. Now we can denote the lateral displacement. This line, imaginary line, is the lateral displacement. PQRS is the direction along which the ray is refracted. T is the thickness of the glass slab. In this case Rx is the lateral displacement, which is Rx is equal to T sine I1 minus R1 whole divided by cos R1. And also Rx has another expression, that is Rx is equal to T sine I1 into 1 minus cos I1 divided by square root over mu square minus sine square I1. Mu square minus sine square I1. Now Rx will have another expression in a special case if the angles or angle of incidence I1 and R1, R2 and I2. If the angles I1 and R1 are very small, in that case cos R1 will be approximately equal to 1, and sine I1 minus R1 will be approximately equal to the angle, that is I1 minus R1. Therefore, Rx will have the expression T into I1 minus R1 whole divided by 1. That is, now we can take common I1 from the two terms. T into I1 bracket open 1 minus R1 by I1. This is a special case in which angles are very small. T into I1 bracket open 1 minus 1 by mu, where relative refractive index of glass slab with respect to surrounding medium, that is mu, will have the expression sine I1 by sine R1. We'll have the expression sine I1 by sine R1, and that is approximately equal to I1 by R1, provided I1 and R1 are very small. So this is the expression of lateral displacement in a special case, for a special case. Rx is equal to Ti1 into 1 minus 1 by mu, which is the lateral displacement of ray of light due to refraction of light, provided I1, the angles I1 and R1 are very small. So now we can go through the revision, that is Rx will have the two expression mainly. Rx is equal to T sine I1 minus R1 whole divided by cos R1, and Rx has another expression in terms of thickness T and angle of incidence I1, that is T sine I1 into 1 minus cos I1 divided by root over mu square minus sine square I1. So Rx has mainly two expressions. These are what? T into sine I1 minus R1 into cos R1, and second one. And we can write down the expression of lateral displacement Rx for a special case, T into I1 into 1 minus 1 by mu. Rx is equal to T into I1 into 1 minus 1 by mu, where the angles I1 and R1, angle of incidence I1 and R1 are very small, and Rx has mainly two expressions, general expressions, where I1 and R1 are not very small, are not very small, are not small.